In this video, we're going to talk about how one takes the type checking rules and translates them into an implementation. The high-level overview of cool type checking is that it can be implemented in a single traversal over the abstract syntax tree. And there's actually two phases here. There's the top-down phase, in which the type environment is passed down the tree. And then there's a bottom-up phase in which the types are passed back up. So we start at the root of the tree with an initial type environment. This type environment is passed down recursively through the various nodes of the abstract syntax tree until we hit the leaves. And starting at the leaves, we use the environment to compute the types of each sub-expression, working our way back up the tree to the root. Let's start our discussion of the implementation of cool type checking with one of the simpler rules in the type system, the rule for addition. And let's just briefly review what this rule says. It says that the type check E1 plus E2, we first have to type check E1, and then we have to type check the sub-expression E2. And both of those sub-expressions have to have type int. And if they do, then we can conclude that the overall expression, the sum of the two sub-expressions, also has type int. And furthermore, this type checking is carried out in some environment. In this case, the environment is the same for the entire expression and both sub-expressions. Just to remind you, there's always an object environment for the object names in scope, a method environment for the methods of the various classes, and we always need to know the current class. Now, how would we implement this? Well, we're going to have a recursive function called type check that takes two arguments. It takes an type environment, and this will be a record. I'm not specifying exactly how that record is declared, but I mean, essentially it's going to have three parts, O, M, and C. And it also takes an expression. And so here we're just doing the case where the expression is E1 plus E2. And what should the code look like? Well, we can pretty much just read the rule and translate directly into code. And this is one of the nice things about the notation for type systems, is it really tells you very, very clearly how to write the implementation from the description. So what's the first thing we have to do? Well, we have to type check the sub-expression E1. And we can see from the rule that the environment in which E1 is type checked is exactly the same as the environment of E1 plus E2. So we just pass whatever our original environment argument was for E1 plus E2, we pass that argument on to a recursive call to type check the sub-expression E1. And that type checking will run, and it will return some type T1. Now, we don't know that T1 is an integer at this point. We're going to have to check that. So we just remember what the type of E1 is. And furthermore, we type check E2. Okay? And that also happens in the same environment. We can see that here in the rule. And again, we'll get back some type for E2, so type T2. And then we confirm that both T1 and T2 are type integer. Now, we could have done the check that T1 is int right away, right after we had type checked T1, and that would have been a fine thing to do. Here, just to save space on the slide, I've put the checks for T1 and T2 all on one line. And if that check succeeds, if it doesn't succeed, presumably there should be some code in here to print out an error message. But if both T1 and T2 are in fact integers, then the type of the whole expression is also an integer. So that's what's returned by this call, by the outermost call here to the type check function. So now let's take a look at a somewhat more complex type checking rule and its implementation. Here's the rule for let with initialization. So we're declaring a variable x of type t, and that's going to be visible in the expression E1. But before we execute E1, we're going to initialize x to the value of E0. And then after we've evaluated the entire let expression, we expect to get back something of type T1. And now for all of that to work out, a few things have to be satisfied, and those are listed as premises here of the rule. First of all, E0 has to have some type T0, which is a subtype of T. And that's to guarantee that this initialization is correct, that x can actually hold something of E0's type. And for the entire expression to have type T1, well then E1 has to have type T1. but that type checking is carried out in an environment that's extended with the declaration for X. And so we also know within E1 that X has type T. So now let's write the type checking case for this. So the function type check is, again, it's going to take an environment as argument, and now we're doing the case for let with initialization. So just reading off the rules and what the conditions are that we have to check, we can see that one of the first things we have to do, or one of the things we have to do, is to check that E0 has some type T0. So we just have a recursive call to type check here. This is carried out in the same environment as the overall expression. So we just pass the environment on to the recursive call, and now we're just type checking E0, and we record its type T0. So the second premise is implemented like this. Now we're type checking E1, and we expect it to have some type T1. But now the environment is different. So we're taking the original environment, the overall environment of the expression, and we're adding a declaration that X has type T to that environment. So we're extending the environment with an additional variable declaration. Okay, so we do that type checking call, and we get back a type T1. Now we have to check that T0 is a subtype of T, so that's a call to some function that implements the subtyping relationship. And if that passes, if that check passes, well, then we're done, and we can return the type T1. And there's a little mistake here on the slide. There shouldn't be a semicolon there. So we just return T1 as the type of the entire expression.